Otherwise, don't. Stress. I really got so
scared to miss it. My binder's staying there now. Wait. Yeah. It shows the board.
I don't know why you did that. Because I can. You can't, bro. Are you recording? Yeah, there's power. No, you didn't say that. Yes, the golf club is fast.
Just watch it live.
Just watch them.
So, giddy up, giddy up. You got an online tonight? I'll see if I have any videos and I'll send them out, all right? But first, we must continue these notes. We left off talking about gravity. Okay, I was going to try to keep rhyming, but I lost my steam. Lost my Steam account. Ah! All right, so. Wait, there's not like an admin in here watching, right? Okay. Somebody from central office might come in and take a gander at what we're learning. So let's blow their freaking minds.
A graduate student came into the English class.
Into who?
Into our English class. She brought a German.
Yeah, I think that's what it is. I don't know if they're coming to this one or not. All right. So, man, I had a lot of visits of ex-students. I just saw Bruce Dickinson, Naval Academy. I saw Josh Payne. He's graduating from Stanford this year. Big dog. Tegan Calvon, I saw her. Tegan Calvon. Lexi Boone. They're all doing STEM majors. And they all have said that it was worthwhile taking this course because it does really help with problem-solving abilities and everything like that. And a lot of them are not taking that's necessarily physics, but it helps out, okay? Anyhow, so let's see this here. Uh-oh. Boom. Now, we left off yesterday talking about potential energy due to gravity, right? Yes? Now, up until this point, when we talked about potential energy due to gravity, we would reliably find it just simply by doing mg times delta H. And the reason being is that work is force times distance. If that force is constant, then you could just take whatever that force value is and multiply it by the parallel distance of which the force points, right? Which in this case would be mg times h, always reliably gives you a dot product that's complete. Now, why were we able to do that and use mgh for our potential energy in the past? Yeah, and most importantly, yeah, the force was constant. And the reason the force is constant when you're near the Earth's surface is because essentially when you're zoomed in near the Earth's surface, it's like it's a flat surface, which means the gravitational field that you're within is basically a uniform field. In other words, these field lines are not getting further apart as you get higher off the ground. Now, there is a point, if you go high enough, where the curvature of the Earth does start to show that your gravitational field lines are actually getting further apart, and thus your gravitational field is weakening. But as long as you're relatively close to the Earth's surface, which is a huge distance in our perspective, you will see a uniform gravitational field. And your G field lines will look like the bars of a prison cell, right? Which, just it's a part of life, so get used to that. Okay. Now, if we move far away, trapped like a rat, you know what I mean? So if we move far away from this, there we go. So this is mass, radius, and then we have some other mass, m, and he is right now a distance r away. This is just representing what the gravity field lines look like due to this planet as you get away. So they're spreading out, right? And that's where that 1 over r squared idea comes in. Now here's the deal. Right now at this moment, let's say that this thing is at rest, all right? So somehow it's being held there. Because in reality, what would happen if this was at rest? Yeah, without something else holding it there, it's going to accelerate towards the planet, right? So let's just pretend that we're at an instant where it's at rest. We'll get to orbits after this. So right now, is there a potential energy state of this system of the large mass and small mass? There is potential energy. Clear evidence of that is what you just told me, that that mass would accelerate towards the planet. Thusly, it would be turning into kinetic energy, right? Now, let me ask you this. Is there a potential energy state if that mass was, in fact, right on the surface of the planet, placed on the surface of the planet? Is there a potential energy state there? There is. There is. Now, you might say, well, wait, but you can't go any closer. Well, that was the whole thing that I was talking about. See, the deal is, the way we used to use potential energy due to gravity when we're near the Earth's surface, we can say something is zero potential energy because for practical application, the change in potential energy is really the only thing that matters to us, right? But it is now going to be very important that we understand that this is very much a potential energy state. There is stored potential energy between these masses, even if it's on the surface. Now you might say, well, why does it matter if it can't fall any further? It matters for some other things that we're about to talk about, okay? So, anyhow. Now, here's what we're going to do. We need to get some way of describing the potential energy that this mass has due to this mass. Now, they're spherical in nature, so it's not like, it's not going to be uniform, all right? Now, I want to ask you, what generally happens to potential energy if you increase the position of something under action by a conservative force? If you increase the position, increase the potential energy, right? Y'all agree it gets greater? So what would be happening to the potential energy state between these then if I move this further out like that? You would naturally want to say it's going to increase, wouldn't you? Hold on, no. You're just moving this guy further away. Okay, so this mass further away. Go in there? So you would naturally want to say, hey, you've increased the position, thusly you've increased the potential energy. Good. Hold on. Slow down. All right, here's the deal. Do y'all see what I'm talking about? However, as Tommy pointed out, something is decreasing as you move further away. What is decreasing? The force, which is also a part of the potential energy state. Y'all see what I'm saying? Because the further you get away, the weaker the force gets. So the question is, what's going to have the greater impact? In other words, is the potential energy going to get greater, or is it going to get smaller as you move further away? Why do you say smaller? Why is that your prediction? Whereas the potential energy is directly proportional to R. Right. Y'all see what he's saying? So what should be the relationship, prediction-wise? Tommy, you want to teach us? Okay. Yes. The relationship for... I'm just giving him a hard time. I'm joking. I appreciate that he is at least one reliable person I have in here. There we go. So, as you move further away, what is happening to the potential energy state as you're moving further away? What's the relationship with potential energy and position going to be? It's going to be decreasing at a rate of 1 over r. Right? Can you all see that based on his reasoning there? Now let's prove it with calculus. So, here's what we're going to have to imagine. Don't worry about the one on the surface. We're going to just start with this guy. Okay? So he's right there. He's at a distance r from the center of this planet. There is a state of potential energy, right? Now, I want you to do some imagination here because, believe it or not, there's a reason why I'm going to describe it this way. I want you to imagine that you are some deity or God, okay? And you have the ability to grab a planet and move it around at your will, okay? So, where would you, this deity, have to move this little mass in order for there to no longer be a state of potential energy? But like, where would it have to be where there's no longer potential energy? You said it's getting weaker as you get further away, right? So where would I have to take it? I'd have to take it to infinity, right? I'd have to take it infinitely far away. Because infinitely far away, what is not going to be acting on it? Force of gravity. Without a force of gravity, without a conservative force, you can't have potential energy. So technically at infinity, the force of gravity would be zero, and thus there's no longer a potential energy state. Okay, I'll kind of get behind that. All right. Now, one thing though, is you are at a very important state in your mathematic, evolution of your understanding of a lot of math here. And you're at a very delicate stage because you're at a stage between infinity being, oh, that's imaginary and it never happens, and it actually really needing to be a concrete number. Let me explain why that is. You're in calculus, yes? Okay. If infinity is not a concrete concept, then the limit itself is of no meaning, okay? Because the limit itself is based around an idea of an infinity, okay? Of this concept. So you have to be willing to accept infinity as very much a concrete value in mathematics if you want to say, oh, okay, I can do calculus. Well, not until you accept the infinity, okay? Another point to be made here is that the infinity, in fact, is treated very much as a concrete value if you are taking limits, okay? So if a limit has been taken, the infinity is treated mathematically as a concrete value. So, for instance, if you were to do 1 divided by infinity with regular arithmetic, what would you taught about 1 divided by infinity? Or it's undefined, right? Right? You learned you can't do that. It's undefined. It's not real, right? Check this out. If you get a 1 over infinity and it's based on a limit, with one of your bounds being infinity, have y'all ever done a bound to infinity in calculus yet? All right. Well, there must be some reason, right? Yeah. So the deal is, 1 over infinity, if it's based on a limit that involves infinity, do y'all know what 1 over infinity then is? It's 0. Concretely 0. Okay? So we have to go ahead and accept that this idea of the infinity is not just imaginary, playing around, ha ha ha, there's really no, it is completely concrete. Okay? So, you are this deity, and you are going to grab hold of this little guy, and you are going to take him infinitely far away. Describe, what are you going to have to exert on it to take it to infinity? You're going to have to exert a force, right? And how much force would you have to exert, at least? What is the minimum amount of force that you would have to exert to move this guy away? Yeah, the value of the force of gravity pulling it in the opposite direction, right? So assuming that you got it moving, you could keep it moving at a constant speed as long as your force, the deity force, was matching the force of gravity that is pulling it back. You with me here? Does that make sense? All right. So in other words, you want the force that you are doing on this to always equal the force of gravity. The main reason you want that, you don't want this to be greater than that, limits, and you don't want to get to infinity with extra kinetic energy. We want to just take it to infinity, and we want it to have no energy whatsoever. No potential or kinetic. You'll kind of see what I'm saying. So you don't want to be accelerating it either. You with me here? Okay. So, we are going to find the work that you do in removing this planet from an energy state. In other words, to take all the energy away from this, you have to move it to infinity. How much work do you have to do? Is everybody familiar with integral FDR? Okay? that is how we find work, meaning F and R need to form a dot product. Do they, in fact, form a dot product in this case? They do, okay? Because they're parallel. Now that we've got that aside, we have to determine, is our force that we're applying going to be a constant, or is it going to be changing? It's certainly changing, because the force that we need to apply is going to be getting what? Small. It's going to be getting weaker, because the further you get away, the weaker the force of gravity is back, right? Do y'all see what I mean? So you're progressively going to have to exert less and less force. Y'all in here? Darn, if only we had an expression for that force we have to exert in terms of R. Do we? Yeah, what is that force that we're going to have to exert? Big G, big M, little m, over R squared dr. Ho, ho, ho! The force we have to exert should be equal and oppositely directed to the force of gravity that we're having to overcome. Does this make sense to everybody? Yes? Okay. Now, what are our bounds of integration here for the work that we're going to do going from here out to infinity? What would be our bounds for R? It would be from R, wherever we started, little r, to infinity and beyond. That's right. When you first heard that statement, you were probably a little kid, right? Oh, that's so silly, infinity. My house is infinity times bigger than yours. My dad makes infinity money, and it was all so cute, right? Did you ever think that the people that probably wrote that script and did all the work to that movie, those Pixar employees, probably some of the smartest people in this whole country? They're hired from absolutely the top schools and top programs, okay? They have to be really smart to make that stuff and to do all those gags. That's why those Pixar movies have humor on so many levels. Dude, the people that are writing that stuff are really smart, okay? Because they can make a gag in an enjoyable movie for a little kid, and they can also make it enjoyable for an adult because it's got enough dimensions to it. Do y'all see what I'm saying? Compare that to some like cheap Saturday morning YouTube cartoon or something, and it's just like, it's idiotic. You're looking at it like, what's going on here? Like, Davis likes it, but, you know, we don't have a whole lot going on yet. So, yeah. I couldn't sit there and watch a Pixar just like he can. You know what I'm saying? Yeah. So, yeah, you want to get a job with Pixar, Google, Amazon, you got to be the top. All right, because that's who they want. Now, check it out. R to infinity. So, what are we integrating here? What are we integrating? What's our variable? R, right? And it's right now it's a 1 over R squared. Can we pull anything out of this? Are there anything that's going to be constant? Yeah, let's get out that big G, that big M, that little m. We're going R to infinity of 1 over R squared dr. Okay? Have y'all, everybody, even people in Calc AB, you have done integrals at this point, right? Yeah. Have you done integration of power rule?
Yes.
Well, then you're A-okay, because that's all this is, my friends. This is integration of power rule. If you want to put it in a friendlier format, you could think, okay, you're doing R to the negative 2 power dr. That makes it a little more friendly to utilize power rule. Y'all see that?
Yeah.
All right, so what's going to be the integral of R to the negative 2? It's going to be R to the negative 1, because you add 1, right? Divided by negative 1, which can be written as negative 1 over R, which is exactly the same thing. Everybody good with that? So yeah, 1 over x squared is negative 1 over x when you integrate it. Okay? Good. So we're continuing on here. Yada, 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 yada. Now, we've got the work that you as this deity have done so far is G, big M, little m. And then we've got negative 1 over R evaluated from R to infinity. So let's go ahead and finish this theorem by finding the difference in our bounds. So we got G, big M, little m, negative 1 over infinity minus a negative 1 over R. Y'all good with that? Because a negative 1 over R is our operator, and then we're putting in minus, and then we have the minus and negative. Check it out, y'all. 1 over infinity. Oh, it's undefined. Nope. Guess what it is? It straight up is 0. No joke. So 1 over infinity is 0. So that means this whole negative 1 over infinity, boop, becomes 0. So what are we left with, the work that you did? Yeah, that becomes a positive. Good. So that is the work that you, as this all-powerful spatial being, has done to move that planet to a state of 0 energy. Right? Cool. Now, here's the deal. Gravity. Gravity did work also, right? How much work did gravity do? Exact same amount as you did, because remember you were exerting equal and opposite forces? So gravity did a whole bunch of work also. Now here's the deal. If we did positive work to something, right? What does positive work do to a system innately? If you have an outside force doing positive work, it increases the energy state, right? Now, well, if we just did something that should be increasing the energy state was a potential energy state, right? And we're increasing it by moving it away. That's literally what we're saying. Well, here's the deal. That means that the potential energy due to gravity is actually defined. Because we want to get to 0, right? So what kind of value would, by increasing it, become 0, approach 0? A negative quantity. So it turns out that the potential energy due to gravity is actually given as negative GMM over R. Now let me explain something. This negative and the way it's explained is disputable. But I will put it to you this way. I'll say this. That negative amount of potential energy that it has is equal to the amount of positive work you would have to do to move that planet to a 0 energy state. Y'all see what I mean? So in other words, if you did positive GMM over R, you're going to reach a 0 state. Y'all see what I'm saying? And thusly it's defined as negative potential energy. Know with me here? So it's becoming a smaller and smaller negative quantity as you're moving away. A larger and larger negative quantity as you're getting closer. That negative is basically the amount of positive work you need to do to remove the energy. To reach infinity. Now, does it need to be treated as a negative in application when we're solving problems? Yes, it does. And in fact, it is as a negative on the formula chart. It's right down below the force of gravity equation, and it clearly has that negative. So I'm going to tell you right now, anytime you're using energy with gravitation as larger masses, as spheres, you must treat gravitational potential with that negative, or all of your problems will be wrong. Okay? Every time you deal with it. And it's on the formula chart as a negative. And I'll show you some reasons why, some application reasons as to why that's so important. So, now what we're going to do, no. All right, I got a quick question. Where is the potential energy state of this mass going to be the largest? Where would it have the most potential energy state if it was right on the surface of that planet? That's its highest energy state. It also happens to be the highest amount of force that it can experience. So the highest energy state for potential energy is when it's right on the surface. Good. So, let's talk about orbital energy. Orbital energy. This is the energy of an orbital system, meaning satellite and the thing you're orbiting. We're going to quantify the energy in that system, okay? All right, so what is total energy? What is the symbol for total energy? E, and what is that always equal to? Kinetic plus potential, right? So orbit energy should be the kinetic energy in the system plus the potential energy in the system. However, somebody brought up something. They said, okay, so let's draw out an orbit. So we've got our larger mass, M, radius, R, and then we got a little mass, and let's just have it as a circular orbit. Okay, we'll deal with ellipses later, tomorrow. So we got radius R, the planet has a radius big R, and we've got a circular orbit here, right? What forms of energy would you recognize in this system, including both the masses? Do you have kinetic energy in this? Yeah, who's got the kinetic energy? The satellite, right? Do you have potential energy due to gravity? Yes, because of the force, mutual force between them, and the fact that there is a position. Now, and the position is not infinity. So you do have those two forms. Now, somebody mentioned, and they're very, very, very clever in mentioning this, somebody said, Mr. Wilson, isn't there also rotational kinetic energy of the planet? Because a lot of times the planet, like if this was the moon and the Earth, the moon's not rotating on its own axis, but the Earth is. Did y'all know that? The moon actually always is facing the same direction, so it's just revolving. So somebody said, well, wouldn't we take into account the rotational kinetic energy of the Earth as well? And let me tell you why we don't need to worry about that. Because for application, the rotational energy of the Earth is not going to be affected by changing the distance of the satellite. So in other words, if I were to increase the orbital radius of this satellite, that has no impact on the rotational kinetic energy of the Earth itself. So for applying this to solve for things, which we're about to do, it doesn't really have an application. Although it certainly, I'm sure, is very important for many other things, okay? So we are going to forego that and treat this middle guy as if he's just the mass sitting there, okay? Y'all with me here? All right. So we've got kinetic energy of the satellite plus the potential energy they share due to position. Let's write out what that total energy of the orbit would be symbolically. What would be the kinetic energy of our, we'll call this V right there. So he's moving with a tangent velocity magnitude V. What is the kinetic energy he has? 1/2 mv squared plus potential energy due to gravity, right? So what's our potential energy due to gravity that they possess? Negative. Big G, big M, little m over R. That's right. Had that negative been foregone, you will never get any of these correct. They will always be wrong. It's got to be negative, okay? Now, so, anyhow, so that's going to actually be a minus right there, right? So, let's consider something here. What the heck is this saying to us? Think about this for a second. Imagine that that right there is 4, and that this over here is negative 20. Okay? Just imagine. Don't worry about the amounts or anything. This is a positive quantity. Do y'all agree? Y'all with me here? Okay. That's a positive quantity. Kinetic energy can't be negative. This is a negative quantity. Y'all did? What does that mean about the total energy compared to just the gravitational potential? With just the gravitational, it's negative 20, right? If you also include the kinetic energy of the satellite, what is your quantity now for the orbital energy? Negative 16. It's weird. Think about this. Remember the whole deity moving the object away? If that planet was at rest, not in orbit, how much energy would the deity have to do a positive work to take it to infinity? 20 joules of positive work would reach it to 0. Do y'all see what I'm saying here? Now, the object has kinetic energy. How much work does the deity have to do to take it to infinity now? Positive 16 joules worth of it, or not joules, that'd be really small planets there. But yeah, now he has to do less work to take it to infinity than he did if it was stationary. What gives, man? What gives? Does anybody have an explanation for that? Why would it require less energy to take an orbiting object to infinity than if it was just stationary and fixed like that and you had to remove it away? Anybody who's paying attention and just listening, please. I'm sacrificing a lot right here of energy. orbital energy. Does anybody know how we got to the moon? What did we do first before we tried to travel to the moon? We went into orbit around the Earth, right? Why did we do that? Why did we go into orbit around the Earth first? And then because what we were able to do is use that kinetic energy to assist us getting to the moon. Y'all see what I'm saying? In other words, if you were to grab this thing right here, you're the deity, it's moving along, and you were to grab it and take it to infinity, you've got some kinetic energy that you can use to help you do that work. It lessens the amount of work you would have to do. Do y'all kind of see what I'm saying? Right. You wanted to redirect the energy in the best way possible. But yeah, because energy is not a vector, so we're getting into sticky territory. But yes, from a vector point of view, you'd want to do it at tangent, right? So, and that's exactly what we're doing essentially for space travel, is we're going into orbit and then blasting out of that orbital path relatively tangent so that we can go and catch another orbit. And that lessens the amount of energy, the amount of work. Because if we just went up into space, first off, we wouldn't be able to stay there unless we were in orbit because we'd fall back down. But let's say we went up in orbit and then all of a sudden we tried to stop ourselves and shoot straight out. That's a lot of wasted energy, man. See what I'm saying? Now, I want to derive out this completely without V involved. How can I eliminate V? Somebody, help me out here. What can I put in for V? Nah. Nah. How can I get rid of V? Well, you were supposed to have done it over the weekend. We need to solve for orbital speed of a circular orbit. So somebody help me. How do I solve for orbital speed of a circular orbit? Help me out. What's the approach? Wow, slow down. I told y'all what you were going to have to do. If this is a circular orbit, where do I start? Yeah. You might want to do this with me, okay? You're going to have to start by stating that in this system, this is UCM. Okay, a circular orbit is UCM. Meaning that the force that is causing that, because he's accelerating towards the center, force that's causing that is what? What force? The mutual force of gravity, correct? Y'all with me here? Is this starting to ring a bell? All right, what can we put in for that force of gravity? Yeah, the universal law of gravitation. You'll dig?
Yeah.
What are we going to see happen here? Satellite's mass goes bye-bye. Remember that the satellite's mass, and guys, y'all going to need to be able to derive this at the drop of a hat. So I'm not going over this again. You were supposed to remember this from last year, and I wanted you to do that over the weekend. So this is your refresh. We got too much new stuff. So we've got that mass is going to cancel. What else? One of the R's cancels. So what does that mean orbital speed for a circular orbit is? Square root G, the mass you're orbiting, divided by the orbital radius. Does that ring a bell? Of course it does. Don't act like it doesn't. Yeah, you have to be able to derive that puppy too, okay? Everybody good? Yeah. Now what do you think we do with this guy? Sub that sucker in there, and we're going to derive out orbital energy in terms of masses and radius. Okay? So let's plug that guy in there. Y'all ready? So we got that the orbital total energy of an orbit, 1/2 little m times root big G big M over R squared minus big G big M little m over R. In other words, that's the potential energy of gravity, which is negative state. And then we've got our kinetic energy with the speed of an orbit substituted in for V. Does everybody follow me on that? Yeah. Should our orbital energy be greater or less in value, in magnitude, than just our potential energy alone? Orbital energy, should that be greater or less in value than just our potential energy alone? In magnitude. In amount, less. It's going to be less in amount. Okay? And let's see what happens. So, we do this. What's going to happen to that square root? Adios. Look what you're doing. These are the same thing, except one's 1/2, the other one's 1. What's 1/2 minus 1? Negative 1/2. That's orbit energy. You will have to use that. That is the inclusion of the kinetic and potential energy state of an orbit. Y'all with me there? Cool? Tight. Tight. Hey, what if I wanted to get orbital period involved back here? Like you remember when I was finding orbital speed? Can I get it in terms of orbital period? So this is total orbit energy, just out of curiosity. So I got it to this, right? How do I get orbital period involved? Y'all remember this stuff? Speed is 2 pi r over the period, right?
Yeah.
Y'all dig? So we just sub that in there. So we got 2 pi r over the period equals root gm over r. So period squared will be equal to 4 pi squared r cubed over gm. In other words, I squared both sides, and then I rearranged the solve, isolated for t. Can y'all do that derivation? Yeah? All right. We did last year, so yeah. All right. What does that show about the relationship between period and radius? Period squared is proportional to r cubed. We're going to talk about that as one of Kepler's laws tomorrow and make a connection. Okay. All right. Now, one more thing we're going to do here. Escape velocity. So, check this out. Back in the 1800s, there were two kind of prevailing ways of thought about traveling to the moon, which we now understood, whether it's possible or not, that the moon was something that could be traveled to. Okay, we had a much greater understanding of what that moon really was, of the distances that we were considering, those kinds of things, right? So, one was by locomotion, right? One was by locomotion, by steam power, was thought that that was a possible way. Obviously, is steam power going to work in space? No, but at least they were thinking that you would need something that could produce a force on it, on itself, off of something, but you would need a track going through space in order to produce that force. You see what I mean? Another prevailing thought was, well, why don't we just shoot a cannon? If we shoot it fast enough, theoretically, right, with enough energy, we should be able to escape Earth's gravity, because they knew that that's what the name of the game was, and hit it. And you know what? The locomotion one, what did that become? What was that the infancy of, theoretically? Rocketry. Yeah, some way of continually exerting and producing energy as a fuel in order to get there, right? Because there was some debate in the infancy of rocketry whether or not that was even going to work in a vacuum, whether those combustive systems were going to be able to work. We found ways around the fact that there is no air, right? We provided ourselves and our engines up there because we need that for combustion, basic chemistry. So, but anyhow, one turned into rocketry. The other one was kind of lost as an idea of how we were going to get to the moon, right? Shooting us in a big cannon and some kind of thing up there. However, it certainly was a part of popular culture. In fact, there's movies about that as the way of traveling to the moon, right? Have y'all, one of the very first motion pictures, Trip to the Moon, a French film, was about a bunch of people getting into a big cannon bullet, and then the cannon firing them and it hitting the moon, and then they were on the moon. And, did y'all see what I'm saying? So, now, is it possible? Well, here's the deal. Technically, yes. If you provide enough initial energy to something, it should be able to escape Earth's gravity. Can anybody tell me how much initial energy we would have to provide to that object to escape Earth's gravity? How much would we have to provide to escape Earth's gravity? That much. We would have to provide at least that much energy, but positive. That's the mass of the Earth times the mass of the object divided by the radius of the Earth. Y'all get that? What is that the energy state of? An object sitting on the surface of the Earth. Y'all see what I'm saying here? Okay. So you see that we would have to provide the object with a positive equivalent of that amount of energy, right? Y'all with me here? Why? What would that do if I gave that equivalent amount of positive energy? It would send it to zero energy state. Where does zero energy state occur? Infinitely far away. Now you might be saying, but you don't really want to go infinitely away. Blah, blah, blah. Yeah, technically you do want to have enough energy to make it infinitely far away. Otherwise you're not going to have enough, okay? Now you got to understand that, yes, the force of gravity from the Earth is going to be negligible after a certain distance, okay? But you made it, all right? The idea is that you have to seek for that value of reaching a zero energy state, which would put you infinitely far away. Okay, I'll kind of get behind this. Yeah? Okay. So in other words, if instead of using rocketry to get into orbit around the Earth, and then from orbit, use rocketry again to slingshot somewhere, we just wanted to straight up brute force it, fire it, boom, right out of there, right? Y'all see what I'm saying? So we have to at least give it that much energy. Where's the major setback in sending a projectile to the moon in this fashion? What's a major setback?
Can't come back.
Well, yeah, you can't come back. Nobody would be in it.
Oh.
That we can assume would not be possible because the amount of acceleration that would be experienced in launching this thing would liquefy the innards of the human body. So no living organism would be in it. It would like literally just be a chunk of lead. Okay? But what would still be the setback? Forget trying to get back or anything. What would be a factor that we would still have to consider? Air resistance. Earth has a very dense atmosphere, okay? And when you move at extremely high speeds through a fluid, what do you experience? Lots of heat. The incredible amount of speed that would be needed to do this would probably, well, not probably, it would completely disintegrate and burn away any material trying to do it. However, do all planets and objects in space have atmospheres? No. You could theoretically do this from the moon. You don't have to worry about an atmosphere then. You wouldn't have to worry about all that heat. You all see what I'm saying? So, assuming that we neglect atmospheric effects, you with me here? We need to solve how fast that velocity's got to be for this mass on the surface of the Earth to go to infinity, to escape the Earth. This is called escape velocity. Now, you might be like, but that's not really a real value or anything. Actually, this math is important because it's a starting place for figuring out how much energy you're going to need to get into orbit. It's a starting place. Do y'all see what I'm saying? So it is actually of scientific importance. Now, let's go ahead and solve for it. How do we do that? Well, what can we say about our energy initial? What kind of energy is this system going to have initially? It's going to have potential energy due to gravity, right? And kinetic. We're going to give it kinetic. What is it going to have when it makes it to infinity? In other words, we want it to have zero energy to start with. That way it has zero energy to end. In other words, when it gets to infinity, how fast is it going when it just gets to infinity? Y'all have a hard time with this stuff, huh? Yeah, it's going to be at rest when it gets to infinity. It was slowing down that whole time, right? The kinetic energy is going to completely go into the work that the deity would have done. Well, now there's no deity to pull it. So you've got to have it all as kinetic energy to start with. Do y'all kind of see what I'm saying? Cool. So, check it. Our initial energy, kinetic plus potential due to gravity, needs to equal 0. What is the expression for our kinetic energy to start with? 1/2 mv naught squared, right? And what is our expression for the potential energy due to gravity that we have at that state? Negative big G mm over radius of the Earth. So that should be mass of the Earth, the radius of the Earth, if we're talking about Earth. But it really could be of any object or any mass. Okay. Y'all with me there? And what does that set equal to? Are y'all starting to see what I'm talking about? Do y'all see what I was trying to conceptually say? Yeah. That kinetic energy, if it equals the potential energy state it's in, it'll get it to infinity. What if you gave it more kinetic energy than that? When it gets to infinity, it'll still have kinetic energy. Woo! All right. So
if there's no force of gravity, then it would just keep going at that speed, right?
if there was no force of gravity?
No, when you get to infinity, there's no more force, like gravity.
Correct. Then it would maintain that speed indefinitely. Yes. To infinity and beyond. Ooh, there's a little bit of meaning behind that one, isn't there? Think about that. Think about that. Anyhow, so you could make a whole literary argument on that one. So we've got now to solve for V naught, which is going to be our escape velocity, right? You with me? So we've got 1/2 little m V naught squared is equal to big G, mass of the Earth, times a little mass divided by the radius of the Earth, right? Uh-oh, what do we see cancel? Yeah, it don't matter what the mass is. That's not going to determine the escape velocity, okay, of the thing you're launching. Mass of the Earth, definitely. So V escape is going to equal what? 2 times the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. Somebody find me that value. What is the mass of the Earth? It's about 6.3 times 10 to the 24th kilograms. Write it down. Somebody solve it. 6.3 times 10 to the 24th kilograms. The radius of the Earth is about 6 times 10 to the... Is it 11? In meters? I don't think so. Is it? I think it's 6 times 10 to the 6th meters. No, it's got to be, wait. 6,000 kilometers, so it's... Oh yeah, that is 6 times 10 to the 6th. Yeah, all right, cool. So the radius of the Earth is 6 times 10 to the 6th meters. What?
What's G again?
Oh, G, 6.67 times 10 to the negative 11. He got it. He beat you.
Yeah.
So, what do you get as V escape?
11,000.
11,000 approximately meters per second. Whew. That's definitely cooking, okay? You launch anything at 11,000 meters per second through this dense atmosphere, it's going to turn into a fireball that's going to turn into nothing really quick, okay? It's going to disintegrate. So, have y'all ever read any of the poem by Lord Byron, Don Juan? Oh, there is an incredible line in there about traveling to the moon. One of the most prophetic things ever written about traveling to the moon. And this was written in the 1810s, 1820s, somewhere around the time.
19th century.
Yeah, but around the same years that Frankenstein was written and published, or written, not published, by Mary Shelley. Mary Shelley was a very close friend of Lord Byron. But the deal is, a beautiful prophetic statement about Newton and his theory of gravity, and about it one day taking us to the moon, and all. Oh man, it's just I can't. I need to memorize it because I like memorizing cool stuff and reciting it. But it is really gnarly. And Don Juan as a poem is one of the best pieces of English literature. So check it out if you can find it. It's like a long poem kind of deal. It's very good.